Compton was able to derive a formula for how much the wavelength of a scattered electromagnetic wave, or photon, should be shifted from its incident electromagnetic wavelength when it scatters off of an electron. He derived this formula using simple considerations of momentum and energy conservation and treating the photon as a billiard ball. I want to go through this derivation now and see where this formula comes from. So in order to derive Compton's wavelength shift formula, we have to view the photon as colliding with an electron that's approximately free inside the atom. In other words, it's not bound very tightly to the atom itself, and it's also stationary. It was derived using what we know about photons, that is that they have an energy equal to Planck's constant times f, the frequency. And since velocity is wavelength times frequency, we can also write that E is hc over lambda, or P, which is E over c for a photon, is going to equal h over lambda. So we know the energy of the photon, we know the momentum of the photon. And in the collision, Compton argued that we must have three things. First of all, we have to have conservation of energy. So if we have a photon coming in and striking a stationary electron, we have to have the initial energy equal the final energy. For the initial energy, we have just the energy of the photon, and we have the energy of the electron, which is at rest. So that's going to just be its mass. The final energy will equal the energy of the scattered photon, which may not be the same as the initial photon, plus the outgoing energy of the electron. He also argued that we have to have conservation of momentum in both directions of x and y. So in the x direction, we have to have the initial p sub x equal final p sub x. If we write that in terms of variables we had before, the photon was initially traveling in the x direction, so it's just p gamma, and the outgoing electron has a momentum p sub e and is traveling in some direction phi with respect to the original direction taken by the photon. So its x component momentum will be p sub e cosine phi. The outgoing photon has a momentum p gamma prime, and it's leaving at an angle theta. So its x component momentum will be p prime cosine theta. We also need conservation of momentum in the y direction, and so we have to have py initial equals py final. And py initial is 0 because the original photon is traveling in the x direction only. The momentum in the final direction, momentum in the y direction, is equal to the electron's y momentum component plus the photon's y momentum component. So these become a set of equations which we can use to solve for the outgoing photon's kinetic energy. There are actually several unknowns in here. We don't know the outgoing energy of the photon, we don't know the outgoing energy of the electron. We also don't know their momenta, but these are related to these energies because square root of square root of p squared plus square root of m squared is equal to e. We don't know these two angles here, phi and theta, as well. So we in fact have four unknowns, the two momenta and the two angles. We're going to try to get rid of a couple of variables that we don't know about and don't care about, namely the electron momentum squared and its outgoing angle phi. We can write down that the electron momentum squared is equal to its e squared minus its mass squared. But using the conservation of momentum formula from the previous page, we can also write down that its momentum squared is equal to the square of the photon momentum plus the square of the outgoing photon momentum minus 2 times their product times cosine theta. If we insert the energy conservation equation number 1 from the previous page into equation A, then we have a way of getting rid of the electron energy in terms of just the incoming and the outgoing photon energies and the electron mass. Now we have two equations for the electron momentum squared, equations A and B, and we'll set them equal to one another and thus get rid of the electron momentum squared. And we have the right-hand side of equation B equal to the right-hand side of equation A. Notice that the only things left now are theta and the incoming and outgoing photon energies. Nothing to do with the electron at all. Squaring out the right-hand side of this expression, we have the difference in photon energy squared plus the electron mass squared plus 2 times the difference of energies times the mass times minus then the term with the mass squared. And we'll need to square this out one more time. We'll need to square out the first term in parenthesis here. And then we get the sum of the two energies, the sum of the energies squared, the incoming and the outgoing, minus 2 times their product. There's the electron mass squared again, plus 2e minus e prime times the mass of the electron minus mc squared again. Now, the good news is some things will cancel here. First of all, notice as I went through with the red line here, the two electron masses squares cancel one another. The other thing to notice is that on the left-hand side of this expression are a bunch of photon momenta, incoming and outgoing. But P times C for a photon is just equal to E. So energy of the photon squared is equivalent to that right there. And those two things cancel on the two sides of the equation. Likewise for E prime, that's equal to P prime times C. So in green, we can cancel out those two terms in the equation. So now on the left-hand side of the equation, I only have one term left. But it's, again, 2 times the product of momenta times C squared. That's related to this thing right here on the right-hand side of the equation, 2 times the product of the energies. I'm in fact going to move this over and remember that P times C is equal to an E. Then we have 2 times the product of incoming and outgoing photon energies times 1 minus cosine theta is equal to twice their difference in energies times the electron mass. I can factor this a little bit more and divide both sides by mc squared, and then divide both sides of the equation by the product of the energies. That's useful because on the right-hand side I see I have two 1 over energies here, 1 over the incident energy, 1 minus 1 over the final energy. And if I remember that for a photon, hc over lambda is an energy, I can write this as this right-hand side of the equation is just lambda prime minus lambda equals hc over mc squared, 1 minus cosine theta. That's Compton's formula. And you can see it was just derived using conservation of momentum in both x and y and conservation of energy, assuming that we had an electron that was essentially stationary and it was not tightly bound at all to the atom. It was just freely able to move.